This is Mr. Sidney Lobo of the Tata Power Company. Mr. Lobo joined Tata Power in December 2008 as Head of Sustainability and then was promoted to Head of Clean Technology Projects. He and his team are evaluating renewable energy technologies, distributed generation systems, improvement of operational efficiency, and other clean technologies. Mr. Lobo.
So, thanks Tarunjit for that introduction on the entire fly ash space. To tell you, I'm from a power company, so let me kind of just tell you what the utility does. We generate power, so ash is not our core competence or our business. But still we are messing around with ash, and I will kind of talk about some of the technologies that we've worked on, we've developed with partners, and why are we doing that. One of the areas which Tarunjit didn't touch upon, and I will kind of briefly tell you what the operation of a power plant is. Yes, coal is burnt in the boiler, and there are two forms of ash generated. One is the fly ash, the other one is the bottom ash. And about 80% is the fly ash, which is collected in electrostatic precipitators, and you have different fields wherein you can collect it in the dry mode. And 20% of the bottom ash remains there, which is really hot, and that is cooled down with water and it's kept in an ash pond. So we've looked at both these guys, the 80% as well as the 20%. And let me talk about some of the things that we've actually done. We looked at, typically, you have ordinary Portland cement and you have pozzolanic Portland cement. And the rule, we are governed by rules, in all the aspects, utility and all other aspects. About 35% is permitted by the government of fly ash to be added to ordinary Portland cement in order to make it pozzolanic Portland cement. But in the market, only about 28% is added. They don't add complete to the maximum limit for reasons that are, with reference to the operational efficiencies of the power plant. As you mentioned, there may be some unburned carbon and those kind of aspects, plus the quality in terms of the fineness. So what we did is we said, okay, this rule does exist. Yes, we are not touching 35%, but let's look at the overall aspect. If we can chemically and physically activate fly ash, by adding certain chemicals and then kind of grinding it further, and we could push it up to 60%. We added about 60% of this chemically and physically activated fly ash to OPC to get the same strength that 100% OPC would have got. Now, the advantage of this is if you look at the overall so-called CO2 emissions of the power plant together with the cement plant, then the overall CO2 emissions come down. Because I have activated 60% of that fly ash and pushed it into OPC, so the entire clinker making of that 60%, that CO2 is eliminated. And it adds value to the power plant as well, because even though I generate ash, I'm not going to give it free. I'm going to charge something or the other. And that's one of the things which we did. We kind of converted 20 tons of our ash, chemically and physically activated it, and we built a road of about half a kilometer. And vehicles are moving on it, everything is fine, and it actually gave us more strength than the design strength. We had designed it for M50, but it gave us a grade of nearly M70. Now, I don't know why did that happen. It could be that, the chemicals were more or something like that, but the results are positive. Now, this is something which we've demonstrated, and we are not the guys. I'm a utility. I'm not the person who's going to commercialize it. So it's a technology which is available, we've demonstrated, we've done a demo. It's someone else who has to take it and commercialize it. We also worked with one of the CSIR institutes of India, and we made geopolymeric cement. Now, geopolymeric cement sets very fast, as compared to the other cement. Within 48 hours, a road is ready. It's ready to be driven. So we again took our ash, this time with our Indian coal ash. We made geopolymeric cement, we made concrete, and we again did about slightly more than a kilometer road within our premises, and it's been subjected to heavy traffic, with coal trucks moving on it. and it's performed to its standards or to the expectation or more than the expectations. A biggest advantage of the geopolymeric cement road or geopolymeric concrete is that we can concrete a road or a pavement, and as I said, within 48 hours you can open that road for traffic. So it's not that you have to wait and cure it for 28 days so that it gains its ultimate strength and you have traffic jams and things like that. Now, why did we do all this, or why are we doing this? And why isn't it working, or why isn't someone commercializing it? The challenge is in the policy. And the biggest consumer of cement is the infrastructure space, which is roads, things like that. And everywhere the policy says that you will make M25 or M50 grade concrete as per IS so and so, Indian standard so and so. And when you go to that IS standard, it further says that the cement that you're going to be using is to be as per IS so and so, which clearly specifies that the cement has to be made by the clinker methodology. So there is no policy, there are no rules, there are no regulations, or there is no framework for the utilization of this kind of material that we've made, or this kind of technologies that we've demonstrated. But it will happen sometime, and the reason, obviously we'll have the first mover advantage by demonstrating that, and someone can take it further and commercialize it. There was this challenge recently about mining of sand. So we looked at making sand, artificial sand, out of fly ash, to the desired grain size. We did that, and the only challenge or the only problem which we faced was we had to sinter it at nearly 1000 degrees Celsius. So after making the entire sand beautiful, like mustard grains, just perfect round, but the landed cost was nearly 10 times that of the sand that was coming. So we said, economically it's not working, technically it's viable. So we went back and said that, hey, I already have bottom ash which is sintered at 1000 degrees Celsius, so why not utilize that? So we took the bottom ash and we graded it. We did a little bit of grinding to break the big clumps, and we looked at what is the classification of sand. We classified that bottom ash, and we made a mortar of cement, bottom ash, and natural sand. And we could replace nearly 50% of natural sand and get the same finish on the surface of a wall with the bottom ash. So what we were thinking, or our long-term aim, was that if you could have it in cement, just in bags, that this is your ready-mix mortar, just add water to it and use it. So that's the so-called idea. But part of my bottom ash will also get utilized as a commercial commodity. And it will also save the mining of river sand, which some places has created a lot of problems. That's another thing that we worked on. Recently, as Taranjit mentioned, low volume but high value. So we said, okay, in India at least, we paint our buildings on the outside. Let's say once in 3 years, once in 4 years. So we made a fly ash based cement paint. And we tried it out, we've applied it and subjected it to the abuse that a building has to go through, with water and dust and things like that. And now we've asked our sister company, one of our sister companies in the group, Tata Pigments, to kind of take a look at that in more detail, because that's their core competence. So this is something which we made, we demonstrated, and we've asked them, why don't we take it further to commercialization? Because, I may not utilize a whole lot of ash, but it will add value, to the little bit of ash that's going out of my premises. The use of fly ash for rails and embankments, there are certain rules and regulations. They have their graph that it has to be within this particle size. And that's one of the challenges that is there to address, but yes, it can be done. Fly ash bricks, aerated, cement concrete bricks, we've done all of those. Technologies are all available, but as Taranjit mentioned, it is the logistics that kills the entire product. In Bombay, just about 50 kilometers out of this city, you have a brick kiln, which may not be in the organized sector. He's making clay bricks. So the urban center, which is the consumption point of these bricks, the landed cost may be about 5 rupees for a clay brick. My manufacturing cost for a fly ash-based brick may be less than that, but transporting it from my power plant to the consumption point just doubles the cost. It just doesn't make sense. So what we've looked at, or rather what we've done, we've said that okay, in the communities around our power plants, where we have thermal power, we've given these small brick making machines to the community and we've asked them to make bricks so that part of my fly ash goes, it's a community based system wherein their economy or their status can grow, and it's up to them to kind of proliferate their business and see what is beneficial for them. We lay a lot of cables because we have to send power, so we lay cables, and on top of the cables we are mandated to put what is called as a cable warning tile so that nobody digs into it and gets short-circuited or whatever. So we worked on modifying the existing cable warning tiles by changing the mesh, by changing the entire property or the entire composition of the tile so that it gives the same strength but utilizes a significant amount of ash. So part of my ash goes off and it becomes a captive use for me, as well as it could be replaced and utilized by anyone else in the market who has to lay even gas lines or whatever to cover the infrastructure. Then now we are looking as typically ash has alumina, silica, and magnesium, calcium. So we are working with one of our technology partners to see if we can extract these minerals out of it, and see what is the value. Prima facie, it looks like it's a good business. At the end of the day, there would be some residue which then cannot go into the cement industry or anything, and that residue would go into a mine filling or something like that. But the value that comes out of extraction of materials is so high that based on the preliminary number crunching, a 100-ton per day plant, the recovery is, the financial recovery is just about 4 years or so. 3 to 4 years, you recover everything based on the prices of the minerals that are on the market today. So in all of this, these are some of the things that we worked on. We are working with one of our sister companies in the automobile industry to utilize the ash for composites. Now they need a very fine grade of ash. So what we have done is we have the capability to extract, the very fine grain ash from different fields of the electrostatic precipitators. So that's what we are supplying, and we've done preliminary tests with them. And it looks, you just cannot make out that, this is a composite with ash and this is a composite with the other filler material. So we are working on different technologies to make ash as a value-added product. And even though it is something which we generate as a part of our business, ash is not our core competence. So what we are looking at and why are we developing these technologies is because we would like it to add value to our customer. It should not be a cost center to the power plant. Thereby, we have to increase our tariffs. As long as ash can stand alone on its own and not be a cost center, we are perfectly fine with it. And it's for the other industries, be it in the cement or in the concrete or whatever the other industry, it's for them to take these technologies forward towards commercialization. So these are some of the things that we've done on ash, and I'll be more than happy to answer any questions that anybody